Section 1.5 Solution Sets of Linear Systems. Homogeneous systems. A homogeneous system is an equation of the form matrix A times vector x equals the zero vector. In this section we're going to be looking at the solutions to both homogeneous systems and to non-homogeneous systems. Let's look at an example here of a homogeneous system. We start with a system of equations. Suppose we have this system of two equations shown here. X sub 1 plus 10x sub 2 equals 0, and 2x sub 1 plus 20x sub 2 equals 0. Now, this can be converted into the corresponding matrix equation, matrix A times vector x equals the zero vector, where the matrix A is going to be the matrix 1, 10, and 2, 20 for the rows, and the vector x is going to be the column vector here with two entries x sub 1 and x sub 2, and then on the right hand side of the equation we have the zero vector with two zeros in it. So this is a homogeneous system. This is a perfect example of a homogeneous system. Now, when we look at homogeneous systems, we have a fixed matrix A on the left hand side, and on the right hand side we have the zero vector. But the part that's variable here is this vector x. We want to know what are all the vectors x that satisfy this equation. Give me all the pairs of values x sub 1 and x sub 2 that make this a true equation. And one of the things that always happens with these homogeneous systems is that the zero vector, when we plug it in for x, when we use 0 as a replacement for x, it's always a solution to this type of system. So while there usually will be many solutions to a homogeneous equation, one solution that you can always count on is this trivial solution of the vector x equals the zero vector. This is always a solution to a homogeneous equation, whether you have more solutions or not. So we always know that the zero vector will be a solution to a homogeneous system. And so the question becomes, do we have any non-trivial solutions? That is, do we have any solutions that are not the zero vector? And so that's the question we can ask here, and we can pose this type of question for the example on which we were working, where we had a matrix 1, 10 for the first row and 2, 20 for the second row. We could take that and make an extended matrix that represents the entire homogeneous system, and when we row reduce it, we get the extended matrix 1, 10, 0, and then an all 0 row for the second row. Now we know that a consistent system like this with a free variable has infinitely many solutions from our existence and uniqueness theorem that we talked about back in section 1.2. And if we look at that theorem, the existence and uniqueness theorem that we talked about back in section 1.2, the theorem said that if we have a consistent linear system, then the solution set contains either a unique solution, and that happens when there are no free variables, or you have an infinite number of solutions when there are free variables. So in this case here, we have one solution already. We know that the zero vector is a solution. It's the trivial solution. So we know that there's at least one. But according to that existence and uniqueness theorem, if there are more than one solution to this system, then there are going to be an infinite number of solutions, and that's only going to happen if you have a free variable. So, according to that existence and uniqueness theorem, the only time you're going to have non-trivial solutions is if you're going to have an infinite number of solutions, and that's if you have one or more free variables. Alright, so let's look at an example where we calculate the solution set to a homogeneous system. First of all, we take this system and we know there's going to be at least one free variable. Why do we know there's at least one free variable? Well, if you look at this system, it's a system with two equations in three variables. And because you have more variables than equations, you're guaranteed to have a free variable. So there are going to be non-trivial solutions. There are going to be an infinite number of non-trivial solutions. Let's find them by row reducing the matrix. So our first step in the row reduction is to take the extended matrix that represents our system and then divide the top row by 2 and then subtract take the second row and subtract 4 times the first row in order to get a 0 in that first column second row position. And then to finish, once you get that second row as 0, 0, 2, 0, to finish here, you're just going to take half the second row and then add 3 times it to the first row. And now we have a properly row-reduced matrix for this extended matrix that represented our system of equations. So we can go from that now to our solution. I mean, we basically have the solution. We just want to write it in vector form. So let's go to the next slide here and we'll see that solution. Okay, so we started with the extended matrix for our system of equations and we row reduced it to this matrix 1, 2, 0, 0, 0, 0, 1, 0. What does that tell us about the variables x1, x2, and x3 here? Based on the first equation there, based on that first row of the extended matrix where you have 1, 2, 0, 0, when you convert that back into an equation and solve it, that tells you that x1 is going to be equal to negative 2 times x2. X sub 2 is going to be a free variable, and remember we had already acknowledged that there was going to be one of those. And if you look at x sub 3, I mean that second row there, 0, 0, 1, 0, is telling you, when you write that as an equation, that x sub 3 is equal to 0. And so in terms of writing out the solution set to the system of equations, it's all vectors x of the form that you see on the bottom of this page here. You need the first component, x sub 1, to be negative 2 times the second component. The second component is free, and the third component has to be 0. So we can write this as the vector negative 2, 1, 0 times x sub 2. And for purposes of making a picture on the next slide, let's call that vector negative 2, 1, 0, let's call that v. And we'll carry over v onto the next slide. So here is a picture of the solution set to the problem on which we were working. So you have your three-dimensional framework here with the axes x1, x2, and x3. And the solution set to this homogeneous system, ax equals 0, is the line that you see here. Now if I label these points, we could start with the point v, draw that vector into your system, which remember was the vector negative 2, 1, 0 from the previous slide. And the thing about the points on that line is that they're all scalar multiples of v. So if you take any point on that line, it's going to be of the form c, a scalar multiple, times v. So the solution set to a homogeneous system, at least in this case, was the span of a single vector. And the span of a single vector here is going to be a line through the origin. In this case, in three-dimensional space, because it was a three-dimensional problem. One thing you want to notice about homogeneous systems is we said that the 0 vector is always going to be the solution to a homogeneous system. So when you graph a homogeneous system like this one, it's always going to contain the origin, just like this particular line goes through the origin. Let's look at another example. In fact, it's very similar to the previous example, but let's emphasize very emphatically here the distinction between this problem and the previous one. It's a very similar system of equations. 3 variables, 2 unknowns, the same coefficients, except in the bottom equation, on the right-hand side, there is a 4 instead of a 0. So this is not a homogeneous system, because you're not saying that the matrix A times some vector x equals a 0 vector. We don't have a 0 vector on the right-hand side anymore because of the presence of that 4. So we're working on a non-homogeneous system here. Okay, so we go through the row reduction process. When we row reduce it, you get the matrix 1, 2, 0, 6, and 0, 0, 1, 2. So what does that tell us about the solution then? After we do the row reduction, once we get this row reduced matrix, we can convert it back into the vector form here. If you take that first row, 1, 2, 0, 6, that tells you that, 1 times x1 plus 2 times x2 plus 0 times x3 equals 6. And if we solve that for x1, we get that x1 is equal to 6 minus 2 times x sub 2. Now x sub 2 is going to be a free variable again, based on its position in this reduced matrix. And then the second row of that row reduced matrix is basically telling you that 1 times x sub 3 equals 2. So x sub 3 has to be 2. If we take that solution and separate the variable and constant components here, the constant components are going to be a 6, a 0, and a 2 from top to bottom, and then the variable components are going to be negative 2x2, x2, and 0. And when we factor out the x sub 2, that's going to be negative 210 times x sub 2. So we can write the solution to this non-homogeneous system as being the vector p plus x sub 2 times the vector v, where v is the exact same vector we had in the previous example. Okay, it's the same vector v we had before, and p is this constant vector that in this particular case is 602. P is the vector 602. So this v is the very same vector v we had for our homogeneous system. And there's definitely a connection here, and we're going to explore that connection as we move into the next couple of slides. So here are the solution sets to the last two examples, both the homogeneous system and the non-homogeneous system. And what's the relationship here? Well, the homogeneous system had a solution that went through the origin. The non-homogeneous system had a solution that didn't go through the origin. And in addition to, whether or not they go through the origin, because they had the same coefficients on the left-hand side, because they were using the same matrix A, as we were calling it, because these were using the same matrix A, the solution sets to the non-homogeneous and homogeneous systems are parallel. Okay, so here's a recap of those last two examples with the accompanying picture. When we solved the homogeneous system AX equals 0, the solution was x2 times v, where x2 is the free variable and v is the vector negative 210. And so the solution, as you can see in the picture, it was the parametric equation of a line that passed through the origin and it passed through vector v. When we moved on to the non-homogeneous system, AX equals b, where b is not 0, not the 0 vector, then the solution was a vector of the form p plus x2 times vector v, where again x2 is the free variable. Now this is the same vector v that we had for the homogeneous system, and so this is the parametric equation of a line that passes through p and goes in the direction of v. And so by going in the direction of v, you're getting a parallel line to the one that was the solution for the homogeneous system. So the solutions to the homogeneous and non-homogeneous systems are going to be parallel when we use the same matrix A for both. Here's the generalization of what we did in those last couple examples. Theorem 6. Suppose the equation matrix A times vector x equals vector b is consistent for some given vector b, and let the vector p be a solution. Then the solution set of the non-homogeneous system AX equals b is the set of all vectors of the form vector w equals p plus v sub h, where v sub h is any solution of the homogeneous equation AX equals 0. So we can use any solution from the homogeneous equation, and then all the solutions to the non-homogeneous equation are going to be of the form p plus that solution. Let's see this theorem in action one more time, but this time it's going to be a little bit different because for the previous examples we had a system of two equations in three unknowns. Here we have a system of one equation in three unknowns, and so the solution set is going to be a little bit different. Last time with two equations and three unknowns, the solution was a line. This time with just one equation and three unknowns, the solution is going to be a plane. And so we're comparing the solution sets to these two different systems of equations where each system is essentially just one equation. So the first system is the homogeneous one, the second one shown here is the non-homogeneous one, and the solution set to each should be a plane. So let's see what this looks like here. If we take that first equation, make the augmented matrix, and row reduce it, we end up with 1, -2, -2, 0. When we take that solution and put it in vector form, x2 and x3 are free variables. x1 is dependent on those two. And so we end up with the solution x2 times the vector 2, 1, 0 and x3 times the vector 2, 0, 1. Let's compare this with what we get in the non-homogeneous case. Here's the same question, except on this slide we're tackling the non-homogeneous version. So let's create the augmented matrix for that equation. 2x1 minus 4x2 minus 4x3 equals 6. Right? This is the non-homogeneous one. When we row reduce it, we get the row 1, -2, -2, +3. And when we write this equation in vector form, again, variables x2 and x3 are free. The variable x1 depends on those two free variables. And when we solve for x1, we get that x1 is 3 plus 2x2 plus 2x3. And when we separate this into multiples of the free variable and a constant, we get the following. We get that this is x2 times the vector 2, 1, 0. We get x3 times the vector 2, 0, 1. And we have a constant vector as well. The only non-zero part is in that first component, so it's 3, 0, 0. So you can see now when we compare the two solutions, the one for the homogeneous system and now this one for the non-homogeneous system, they are very, very similar. The only part that was different was the constant vector that you see on the right-hand side, this 3, 0, 0. And so that means when it comes time to actually look at the picture of these solution sets are going to be two planes, first of all, and they're only going to differ by a constant. So let's look at that picture. Let's go to the next slide. Here is the picture of those two solution sets. For the homogeneous system, we have a plane, and the plane, of course, because this is a homogeneous system, this plane has to go through the origin. So of the two planes here, the one on the left that goes through the origin, that's your solution to the homogeneous system. The solution to the non-homogeneous system, coming from the same matrix A, because we use the same matrix A, it's going to be a parallel solution. So if the homogeneous system is a plane through the origin, the non-homogeneous system using the same matrix A has a parallel plane for its solution that does not go through the origin.